Hello everyone and welcome to this video. In this video I will talk about enthalpy changes, exothermic and endothermic reactions. In the next video I will talk about how to measure the enthalpy changes using calorimeter. You have two types of reactions. And reactions that will give off energy when it happens, and another reaction that will take energy for this reaction to happen. So we have what we call exothermic and endothermic reactions. The exothermic reaction usually accompanied by a releasing of energy. You could see that by measuring the temperature of the reaction at the beginning of the reaction, you will find it increased at the end of the reaction. Now in this example you could see we have magnesium and sulfuric acid that react together, and magnesium sulfide is formed, and at the end of this reaction actually energy is released. So at the end of the reaction the container of your reaction is actually have a higher energy than at the beginning of the reaction. The endothermic reaction, on the other hand, the reaction would absorb energy from the surrounding. Example for that, if you dissolve ammonium chloride in water, what will happen is a dissolution of the ammonium chloride into ammonium ions and chloride ions, and the temperature would drop at the end of the reaction from the beginning of the reaction. So if you hold your container, you will find it cooler at the end of the reaction, cooler than when you started your reaction. Now, we said that there are reactions which are exothermic and there are endothermic reactions. The heat contained within any chemical reaction, we will call it enthalpy change. And the enthalpy change will be the internal energy of any substances. You have to remember there is a big difference between the temperature and the heat. The temperature is actually the measure of how hot substance is. You can measure the temperature in Celsius or you can measure it in degree Fahrenheit. On the other hand, the heat would be the measure of the thermal energy or the contained energy within my substance. I will measure it in joules. Now, because we cannot just measure the heat directly of substance or the energy contained in the substance directly, we will measure the temperature, and this will reflect the change of my enthalpy, which is the delta H. So the delta H in that case would be the energy exchange between a chemical reaction and the surrounding. At constant temperature, this is what I can calculate using this formula. So I have delta H would be minus MC delta T, where in that case M would be the amount of my substance in kilogram. C will be what we call a specific heat capacity. So the specific heat capacity is the energy needed to increase the temperature of 1 kilogram of my substance 1 degree Celsius. The last factor is the delta H, which would reflect the change of my substance. So this specific heat is actually have a specific quantity that we just can obtain it from any specific heat tables, a parameter that doesn't change. But the T would reflect the energy of my substance, because now the T that I'm calculating, the T final minus the T initial. This would give me the change in the temperature of my reaction. So this difference multiplied by specific heat multiplied by the mass would give me what we call the enthalpy change. Now again, you have to remember the enthalpy change itself should be the enthalpy of my products minus the enthalpy of my reactants. Now the unit of enthalpy would be kilojoules per mole. Now for the enthalpy change itself, it will be the change in the temperature from the beginning of the reaction to the end of the reaction. The enthalpy change should be the energy exchanging between the chemical reaction and the surrounding at constant temperature. But because we cannot measure energy, we will measure the temperature instead of measuring the energy. So the temperature will reflect the amount of energy of and reaction. Now, if I looked at the enthalpy itself, would be the total energy associated with the material that reacts. So I have delta H This is the change of my enthalpy, and I have only H is the enthalpy of any material that reacted or produced during my chemical reaction. Let's look at it in another way. Now, if I have an energy change from the starting of the reaction and the end of the reaction, I need to calculate the enthalpy change. So what should I do? I will calculate it. So my enthalpy change will be the product, the enthalpy of my product minus the enthalpy of my reactant. I will have two either possible ways. I will have either the product have energy or enthalpy higher than my reactant, or I can have my product have a lower enthalpy than my reactant. If I have the product higher, the enthalpy of my product higher than my reactant, this means I will have delta H with a positive value. This will be an endothermic reaction. If I have my delta H with a negative value, this means my product enthalpy is less than my reactant enthalpy. This means I have a negative value for the delta H, and this will be considered as exothermic reaction. So this one is exo, and this one will be endo. For the unit of the enthalpy change is kilojoules per mole. Now, for any chemical reaction, we can do what we call enthalpy profile diagram. So what is this diagram? It has an y-axis and the x-axis. For the y-axis, it will present the enthalpy of my product and the enthalpy of my reactant. Now, I have either the product have a higher enthalpy than the reactant, and it will be on the top, or I have an enthalpy of my reactant higher than the product, and this will make my enthalpy of my product goes down. For the x-axis, it will show me the reaction pathway. I will have at the beginning the enthalpy, the reaction of my the reactant on the left, and I will have the product on the right. The reactant is either drawn at the bottom, which means it will have a lower enthalpy than the product, or I can draw it if I have another type of reaction, which is an exothermic reaction. I will have it on the top, and I will have my product at the bottom. Also, we write down usually the enthalpy change of this reaction. So you could see here the enthalpy, the reaction pathway, reactants, delta H, products. Now, for the exothermic reaction, if I looked at the enthalpy profile diagram, in here, for example, I have the combustion of methane in presence of oxygen. So you have, because this is a combustion reaction, like I said before, it will be accompanied by a releasing of energy. This means my reactants have a higher enthalpy than my product. And if I look at the reaction pathway, in here I have the reactant is drawn at the top of my diagram, and the product are drawn at the bottom of my diagram. Now, if I look at the energy, like I said, it is released during this reaction, and the delta H in that case should be a negative value, because I have the product minus the reactant. In that case, this have a lower value. Here, I have a lower value than the reactant, which have a higher value. So this is why we usually write this negative to imply that this reaction is accompanied by a releasing energy. So this means releasing energy. And also it means that I have here an exothermic reaction. Now let's move to the endothermic reaction. My enthalpy profile diagram in that case will show the reactants at the bottom and the products at the top. Because now I have my reactants, in that case I have calcium carbonate dissociation into calcium oxide and carbon dioxide, and this is usually accompanied by absorbing energy from the surrounding. So the energy would be absorbed from the surrounding. This means the product will have a higher enthalpy than the reactant. So if I looked at the delta H in that case of my product minus my reactant, in here this will have a higher value and this will have a lower value. This means I have a positive value for the enthalpy change, and this positive value means I have, in that case, endothermic reaction. Now, if I looked at the enthalpy profile diagram, if I looked at this positive value, it means that I have endothermic reaction, and it also means that my reaction actually absorbed energy. Now, moving to the standard enthalpy change of combustion. If I add this word, which is a standard, this means I'm looking at the combustion, the enthalpy change of combustion of just 1 mole. So if I burn 1 mole or I combust 1 mole of my reactants, in that case, I will call it that the enthalpy change, I will call it in that case standard enthalpy change. So the standard enthalpy change would reflect the combustion of just 1 mole. So my substance in that case will be combusted, and usually this happens in the presence of oxygen, and it always gonna be exothermic reaction. This means my delta H, or the enthalpy change, the standard enthalpy change, because I'm doing combustion for just 1 mole, this means it will have a negative value. Look here, I have 2 reactions, combustion reactions, and I have a negative value. And if I looked at this standard enthalpy change, it will reflect the combustion of just 1 mole of sulfur, and in that case 1 mole of methane. So if I have any reaction and I need to know the standard enthalpy change, I have, if I burn it like a half of a mole or a fraction of a mole, I need to multiply until I get the value that reflect the combustion of 1 mole in order to get the standard enthalpy change. Now, I also have what we call standard enthalpy change of naturalization. This means I will have naturalization reaction, and in this naturalization reaction, 1 mole of water would form. This is why I will call it standard enthalpy change. So the standard in that case will reflect the formation of 1 mole of water, and because it is a naturalization reaction, this means I will react an alkali with an acid, and 1 mole of water would form. This is also an exothermic reaction, and if I looked here at the standard enthalpy change, this value is a negative value, and it reflects the formation of 1 mole of water. Usually what we have in the acid-alkali reaction, a unique equation usually involves the reaction of the hydrogen ions and the hydroxyl ions to form the water. Usually the Cl chlorine atom ions or the sodium ions, we call it spectator ions. This means they do not involve in the chemical reaction. Now moving to what we call standard enthalpy change of solution. In that case, I will dissolve my material, and this dissolution, I will make a solution of my material, and in that case, I'm forming an infinitely dilute solution under standard conditions. So in here you could see we dissolved 1 mole of hydrogen, and this would take out energy from the surrounding. A positive value means endothermic reaction, and this means it absorbed energy from the surroundings. So usually the solution, the formation of a solution, it takes out energy from the surroundings. So I have endothermic reaction. So I had here exothermic reaction for the naturalization, exothermic reaction for the combustion, but for the solution it is an endothermic reaction. Moving to the hydration. Hydration is also an exothermic reaction. So the hydration would be the dissolving of anhydrous salt, 1 mole of my anhydrous salt, and this will give off energy, and I will call this value the standard enthalpy change because it reflects the hydration of just 1 mole of my reactants. So in the next video, I will show you how to measure the enthalpy change using calorimeter, and in that case, I will also solve some problems on how to calculate the delta H of a reaction. Until next video, thank you and goodbye.